So with integration by parts, you can see that we have some integrals that are basically hideous, right? I mean, like, at this point, you have nothing that you can do. If you pull back on all of your resources to this point, and you're like, well, L of x, well, the derivative of that is 1 over x, so that can't be like a u because I have an x there. Like, you're just stuck, basically, when you get to things like this. And so this is where integration by parts comes into play. So this is the formula of integration by parts. It says if you're integrating a function and the derivative of another function, then you can take those two functions multiplied minus the integration of the one function times the derivative of the other. Okay, so what does this mean? Well, this means that I could look at this as two different functions. I could say, well, x is a function, and then the natural log of x dx is another function. And I'm actually looking at the function of this and the derivative of that. And so then I could take the antiderivative ln of x and use it as my v, and take the derivative of u, and I could have a u, a v, a du, and a dv. And then you plug all those pieces in to this formula. So you basically are looking at u and v functions, the derivative of u and v functions, okay? And then you're taking those pieces and putting them together. It's figuring out which piece works best for you that is the more difficult part. And so we're gonna walk through how to figure that out. So you need to know this formula. So this is the formula you wanna get stuck in your brain. All right, and so we'll walk through how to make this work for different parts, all right? So let's look at example 1. Example 1 says evaluate x e to the x dx. All right, that's all fine and dandy, except it's not gonna work unless we separate this and split it into parts. So the first thing they point out is that you could have a combination of different things here. You could say that x is your u and e to the x is your dv, or e to the x is your u and x dx is your dv, and all these different scenarios that can happen, all right? And so that's what we're gonna start doing. We're gonna start playing with it and saying, okay, what works easiest for us? Keeping in mind that we're gonna have to multiply our two functions, and we're gonna have to multiply one of them times the derivative of a function. And so what we're really trying to do, this integration is the hard part. This is just straight multiplication. Once you figure out your functions, you literally just multiply those two. Like, you don't take the antiderivative, nothing. So we really are looking to make this piece of it the easiest thing we can do, and something that we know how to do, okay? So let's look at what were the possibilities. So the first thing that's possible is, and I'm just gonna write out these two. So if I have this, and we'll just copy him so I have it twice. All right, so let's say we have this. Here are my my options here. I could say that x is my u and that e to the x is my dv, because my formula says I'm looking for a u and a derivative, okay? A function and one that has already been derived, okay? So that's my first option. If I do that, so if I say that I have the u as my x and my dv as my e to the x, then that would mean I also need v and I need du. So if I take the derivative of x, what is the derivative of x? 1. If I take the antiderivative of e to the x, what is the antiderivative of e to the x? Just e to the x, right? So that's one of my options. One of my options is that I would have a u of e to the x, of a u of x, and a v of e to the x, and a dv of e to the x dx, right? Those are my first pair. If I did it a different way, so let's say I flip-flopped it. So let's say I rewrote this and I said, no, instead I'm going to have e to the x as my u and x dx as my dv. So let's say I do it that way. Let's say this is my u, and let's say this is my dv. Okay? So then what would my du be? Well, that would just be e to the x, right? Derivative of e to the x is just e to the x times derivative of x, which is 1. But here's my, what about if this is my dv? Well, what's the antiderivative of x? Yeah, so it'd be 1/2 x squared. It seems like I made it more complicated by doing that, right? Because what am I going to have to multiply? I'm going to have to multiply u and v. That's easy. I don't care about that because that's just straight multiplication. However it ends up, it ends up. But I'm going to have to multiply d and v and du and take the antiderivative of it. Well, the v over here, v times du, that's a fairly easy antiderivative, e to the x. Over on this other side, v times du, that is just as complicated as what I started with, right? So this one is much more difficult. So we won't want to do that one. So we're going to set it up the first way. We're going to say, well, my u is going to be my x, which means my du is going to be just 1. My dv is going to be my e to the x dx, which means my antiderivative of that is just e to the x. There's my u, my v, my du, and my dv. That's the hard part. Now we just plug it in, okay? So now we're just going to take those parts and plug them in. U times v, x e to the x, minus the integration of v, e to the x, times u. Well, that's just 1 dx, right? Which I guess I need to put my dx's in there. And now I just take my antiderivative. What is my antiderivative? Well, it's just e to the x. So I end up with x, e to the x, minus e to the x plus c. And that is the integration of x, e to the x dx. That is my answer. All right, so I have some options here. If my u is x squared, then my du would be 2x dx, right? If my dv is ln of x, then my v is ln of x. What is the antiderivative of ln of x? That's derivative of ln of x. Yeah, we don't have one. We don't have an antiderivative of ln of x at this point. Right? I mean, look at all your shortcuts. You can flip back. Look at page 484. Antiderivative. Now, derivative of ln of x is 1 over x, right? But if I have a dv, I have to take the antiderivative. What's the antiderivative of ln of x? We have a problem. So if we set it the other way, u is ln of x. Du, we know that derivative, right? So that would make my dv my x squared. The antiderivative of x squared, while it's not pretty, at least we know it, right, is x cubed over 3. Everybody follow that? And so in this situation, I don't have to worry about trying to pair it up and which one's easier. I actually have a problem if I make ln of x my dv, because I have to take the antiderivative of it. And so I'm going to go with my second route here, because my first one is going to cause a problem. So my u times v, I'm just going to plug it in. U times v, well, that's going to be, I'm going to write it this way so it doesn't look weird when I do the ln of x cubed over 3 ln of x, right? Minus my v. Well, my v in this case is x cubed over 3, right? Du, 1 over x dx. I can actually take that antiderivative, right? I can simplify it. My x's will cancel here. So I end up with the first part, x cubed over 3, ln of x, antiderivative of x squared over 3. Well, that's x cubed over 3 divided by 3, which is x cubed over 9, and then plus c. And so in a situation where you have an ln of x, you're automatically going to be like, yeah, ln of x should not be my dv, because I already have a problem trying to take the antiderivative of the natural log here. Now, if it were the natural log, so if you go back and you do where you could do a U-substitution or something, and you end up having a natural log as one of your DUs, right? When you're doing U-substitution, you can have a natural log in your integration as long as it's taken up somewhere in some other form. But in this case, it's not. There's nothing you can do that's going to make that just go away when you take the antiderivative. And so if you already know there's an issue with a piece of it, that's probably the piece that you're going to derive, not integrate. Right, you want to do your u as your ln of x, because we don't have an antiderivative for ln of x, which means du is going to be 1 over x dx. Then my dv must be the rest of it, x to the 4th dx. And my v is going to be x to the 5th over 5. When I plug that in, I'm going to have x to the 5th over 5 natural log of x minus x to the 5th over 5 times 1 over x dx. These simplify. So I end up with x to the 5th over 5 minus, this is going to be x to the 4th over 5 divided by 5, which is over 25. And then plus c. So first of all, this is definite integration. Second of all, it doesn't seem like I have two things going on here, right? Like, it looks like I only have one thing going on. But the problem is I do not have an antiderivative for arc sine. I have a derivative, right? I have a derivative for arc sine, but I don't have an antiderivative. So for this one, I definitely want my arc sine to be my u. It helps you because you can actually just do the dx as part of your u and dv piece. So in this case, I would say, well, yeah, I definitely want arc sine to be my u because I don't have an antiderivative for that at all. All right. So if I set it up that way, I can say, well, my u is going to be my arc sine. That's easy because I don't know what else to do with him. So that means my du is going to be the 1 over the square root of a squared minus u squared, in this case 1 squared minus x squared. So what does that leave as a dv? Well, that leaves just the dx part. That's all we have left. We've used this part of it. We haven't used the dx. What's in front of that dx? If you don't see a coefficient, what is it? 1. So I do have a really easy antiderivative of that. What's the antiderivative of 1 dx? It's just x, right? And so while it seems like this is not going to be an easy antiderivative, it's actually just a really easy U-substitution antiderivative that we're going to end up having. Okay? Because keep in mind, you're going to multiply the v and the du to take the antiderivative. So I'm going to end up with an x over some weird function that has x squared. It will allow me to do a U-substitution. Okay? So I'm going to say, well, u times v, and I'm going to put the v in front, just its multiplication, it doesn't matter, but just so it doesn't get caught up in the arc sine. So x arc sine of x minus v, which is x, du, which is the 1 over 1 minus x squared. And this is also definite integration. So when you're doing this, you've got to keep in mind this whole thing is from 0 to 1. We're not done with the integration yet. And that first piece is part of the integration. So that matters when you go to plug it back in, or you'll get lost in the shuffle. So U-substitution is actually really simple here. What's my U going to be? Right? What's my du?
Just x.
Negative 2x dx. I don't want a negative 2x. What do I want?
X.
Just x. So what do I need to do?
Take out 1 x.
Yeah, so negative 1/2 equals x dx, right? So this is going to end up being, if I just write it smallly, negative 1/2 u to the negative 1/2, right? So when I take this antiderivative, I leave this alone. I've already dealt with that part. X, arc sine of x. And then I need to do my antiderivative and plug my u's back in. So what's my antiderivative going to be? It's not a hard one, but you have to think about your fractions there. And I would actually go ahead and do this part here. I would actually change this because when you pull that out, you're going to have a minus a negative 1/2 times that. So you can just do that. So we're going to say u to the positive 1/2, right? We have to add 1. Divided by 1/2. What is that? Multiplied by 2, right? So I end up with 1/2 times 2 here, right? So then that just cancels. And my last step before I plug everything back in is to, of course, plug my U-substitution back in. So I end up with x arc sine of x plus, instead of u, I'm going to say 1 minus x squared to the 1/2, or square root of 1 minus x squared. And I am taking that from 0 to 1. And I actually need to plug those in. I plug in a 1, I get 1 times the arc sine of 1 plus the square root of 1 minus 1 squared minus, and don't assume that the arc sine of 0 is 0 because it's not, minus arc sine is 0, but I am multiplying it by 0, so that will zero that out. Just pay attention. The only reason this one zeroes out is because there's an x in front of it, okay? Because think about what arc sine means. All right, plus the square root of 1 minus 0 squared. So when it's all said and done, this guy zeroes out and this guy zeroes out, right? And I get the arc sine of 1 minus 1. And you can actually plug that in and get an answer. Arc sine of 1, that's pi over 2, right? Where what radian gives you a sine of 1? Well, that's pi over 2. So you get pi over 2 minus 1, which is approximately 571. All right, so look at example 4. Repeated use of integration by parts. I actually like these. It seems weird, but I like them. All right, so once again, we're trying to figure out what's the path of least resistance here. And I typically start with the first one as my u just to see, but sometimes, especially with a trig function with sine, because it's just going to bounce back and forth. Like the antiderivative sign is going to be the cosine and the derivative sign is going to be the cosine. You know what I mean? Because they bounce back and forth. So sometimes it's kind of hard to see. But if I were to say that u is my x squared, that would mean my du would be 2x. All right. And then that would leave my dv as the sine of x, dx. And remember, when I take an antiderivative sign, I have to consider a negative, right? So my v then would be negative cosine of x. All right. This doesn't seem to help me, right? It seems like it wouldn't. What it does is it gets you on a path to potentially do integration by parts again, because even if I set it up the other way, I'm still going to have a sine or a cosine and a function of x. I'm just going to have a more difficult function of x. If I take the antiderivative of x squared, I'm getting x cubed over 3, and it's still going to be paired with a trig function. Does that make sense? And so either way, you're going to have something paired with a trig function, make it the easier thing. And so if I do u times v, so I get negative x squared cosine of x minus, and then I'm going to have my v du, right? So I'm going to have negative cosine of x times 2x dx. This is also a problem, right? So I actually have to do integration by parts again. I would go ahead and change this, by the way, to positives there. But I still have a problem. I have cosine of x and a 2x, which doesn't help me at all. However, now I've actually gotten rid of an exponent on that x, as opposed to added one to it if I had taken the antiderivative. So if I do integration by parts again, I can set up the 2x as my u. Du is now just going to be a 2 dx, right? Which leaves a dv of cosine of x dx and a v of sine of x. Now I actually have an easier integration by parts, right? And so then I'm going to rewrite the whole thing using these. I'm going to still keep this one here, negative x squared cosine of x, but now I'm going to replace this guy with yet another integration by parts, okay? So you have to keep in mind that had I not changed that to adding the, it's like had that not been a negative here, so I just want to point this out because of your positives and negatives. Had this not been a negative, you are subtracting the whole thing. But because it was a negative, they're both plus, right? I'm only saying that because when you do integration by parts the second time, you're subtracting a group, which means you're subtracting and subtracting, so you have to distribute that negative through. But it was a negative in front, so it ended up being plus anyway for this one. But I want to point that out because that's a common mistake. So we have plus, and we're going to do this integration by parts. U times v, that's 2x sine of x, minus v du. Well, now we just have the integration of 2 sine of x dx. Well, that's easy, right? What's the antiderivative of sine of x? Negative cosine. So I have negative x squared cosine of x plus 2x sine of x, and it's minus a negative, so it's plus cosine, 2 cosine of x plus c.
So, on the blue part, that's the original first integration by parts, the first part, and then you got that from the second part, the 2x sine.
Right, so technically the pink is the first integration by parts, u times v plus, minus the derivative of v du. And then I had to do this piece of integration by parts, which is what this part is. So then I just brought that down, plus this integration by parts, and then I actually took this antiderivative, and this was my final integration. All right, secant cubed. So once again, this appears to just be 1. However, it's cubed. So I can technically rewrite this 1 like this if I want to. Right? And then all of a sudden you start seeing that you could potentially have something that's a little bit easier to deal with. Because I actually do have an antiderivative for secant squared, right? What is my antiderivative of secant squared? Tangent. So if I make u my secant, du, derivative secant is secant tangent, which means my dv would be secant squared, and my v would be tangent. And then it's going to set me up for basically a U-substitution deal. A little bit. Well, not U-substitution. It's going to set me up for a substitution because it's going to be what I'm looking for. So if I were to write this, I am evaluating the secant cubed of x, right? That's going to equal u times v, secant times tangent, minus the integration of v, that's tangent, times du. Well, that's secant x tangent x dx. All right. Now, I can combine these tangents, okay? So I have the integration of secant x tangent squared of x. All right? Now, this is where you're going to look at all your options. I don't have an antiderivative tangent squared, right? But I do have a trig function that deals with tangent squared, where I can actually get rid of my tangent squared altogether. There's a trig function. What's my trig function? Tangent squared plus 1 equals secant squared, right? Which means tangent squared equals secant squared minus 1. I'm just going to substitute using a trig identity. So I'm going to replace this guy with secant squared minus 1 based on my trig identities. So I get my secant x tangent of x minus, I actually end up with secant cubed of x minus 1 dx. Now, from way back when we started doing integration, if you have a plus or minus within an integration, you can actually integrate each piece separately, which means I can write this integration like this. I can say integration of secant cubed of x, right? And I am subtracting the whole thing. So this is a situation where if I split this up, I have to consider that 1 there to be, oh, this is just secant, sorry. I need to distribute. I distributed that guy. It's a minus a negative, so when you do this piece, you have to change that to plus the integration of secant of x. But I can split that up. The secant cubed and the secant are just individual pieces that I can split up. So at the very beginning, what were we solving for? What does all of this equal? This equals the integration of secant cubed of x. What do you notice about both sides of the equation? They both have a secant cubed of x. I'm going to move that bad boy over. I'm just going to add them over to the other side. Don't forget your basic algebra, okay? Your basic algebra says this is an equation, so whatever I do to one side, I can do to the other, which means I can add a secant cubed of x right here, and I can add a secant cubed of x right there. Right? Because he's my problem, isn't he? So he cancels out, and I actually have 2 of the integrations of secant cubed of x equals secant of x tangent of x plus the integration of secant of x, which I have, by the way, an antiderivative for, don't I? What's the antiderivative of secant? Should be the natural log of secant plus tangent, right? So I end up with 2 secant cubed of x equals secant x tangent x plus the natural log of secant x plus tangent of x plus c. All right. I don't want 2 of them. How do I get that 2 from one side to the other? Divide everything by 2 or multiply by 1/2, right? So you multiply by 1/2, so you end up with 1/2, 1/2. You do not have to multiply the c by 1/2 because it is a constant, so a constant or a constant times 1/2 is still a constant, and that is your answer. Your answer is 1/2 secant of x tangent of x plus 1/2 natural log secant x plus secant plus tangent x plus c. That whole thing is your answer. This kind of gives you some integrations, like common integrals that are used for parts. And they kind of show you, which you'll see on your worksheet, that you see a lot of these kind of in the process. I didn't throw any arctangents on here just yet. Natural log might show up, but I don't know if it showed up on your worksheet. It'll probably show up on your test review. Natural log's a good one too. And then e to a function of x with trig functions as well. Sometimes happens, So for this one, because e to the x is going to be the same whether you derive it or take the antiderivative, that's going to be your dv. Because if you do the x cubed as your dv, you're going to make it more difficult, right? So for this one, I had my u as x cubed, my du as 3x squared, my dv as e to the x, and my v as also e to the x. And then of course I do u, v, v du. So I'm going to say, and x cubed e to the x minus e to the x 3x squared dx. And this is actually, all right. And then I have to do it all over again, right? So on the second time around, I made my u, my 3x squared, my du 6x, my dv e to the x, and my v e to the x. So I have x cubed e to the x minus, and this whole thing is subtracted, 3x squared e to the x minus the integration of e to the x 6x dx. And I had to do it again because, you know, just for funsies. All right. So I had to do the same thing with this piece as well. I think my Apple Pencil just died. Nope. It's not writing. Okay. All right. So I'm going to distribute this. Oh my goodness, it is not. Oh, okay. I was like, something's wrong with my pencil. It's actually the program. All right, so I'm going to actually distribute that negative through. So I have x cubed e to the x minus 3x squared e to the x plus, and then I'm going to do this here. So on this end, my u is my 6x, and my du is my 6. My dv is my, again, e to the x, and my v is my e to the x. So I have 6x e to the x minus e to the x times 6 dx. Now I can just take the antiderivative finally, right? And so I finally get to the point where I can solve this guy. X cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. So I would set it up just like I did before. U is x cubed, du is 3x squared, dv is sine of x, and v here is going to be negative cosine of x, because remember, the antiderivative of sine is negative, the derivative of a cosine is negative. So when you're going back and forth like that, that's what you need to do. All right, so we're going to go, so I just pulled the negative in front just because it was easier. Negative x cubed cosine of x minus the integration of negative cosine of x 3x squared dx. All right. In this case, you can pull that negative over, and you can, when you pull that negative out, it turns that. Okay? Minus the negative. You can pull the negative out from in front of the cosine, -1, and so you end up with minus a -1 times that whole thing, and so those will change to positive. And just like the one before, we have to do this all over again. So I made my u, my 3x squared my du, my 6x. My dv this time was cosine of x, and my v was sine of x. And so now I'm going to do this again. Negative x cubed cosine of x plus 3x squared sine of x minus the integration of sine of x times 6x dx. And one more time. I'm going to say u equals 6x, du equals 6, dv is sine of x, and once again, my v is negative cosine of x. All right, so I'm going to say negative x cubed cosine of x plus 3x squared sine of x minus, and I have this whole group here, negative 6x cosine of x minus the integration of 6 sine, v du, cosine, negative 6 cosine of x dx. All right. Pay attention to your positives, negatives. If I pull this negative 6 out, that's going to be a positive there. But then when I distribute, that's going to be positive, and that's going to change that back negative. So, do you make sense? So these two negatives made it positive, but when I distributed negative, it made it negative again. All right, so I have negative x cubed cosine of x plus 3x squared sine of x plus 6x cosine of x minus, the antiderivative of cosine is sine. So 6 sine of x plus c. And that is your answer right there. This one, you obviously want your u to be the ln of x because we can't take the antiderivative of ln of x. That's the whole problem here. So my du is going to be 1 over x, which means my dv is just the dx, and my v is just x. And so I'm going to say uv, I'm actually going to put the x in front of the ln of x just because it's easier, minus the integration of x times 1 over x dx. So I'm going to simplify this to just be 1. So I have x ln of x minus x plus c. Sometimes it helps when you have this to like write the 1. Like if you see that it's just one piece, to write like times 1 dx, and it kind of in your brain makes you remember to actually do the integration of it. Okay, so again for this one, you want your u to be your ln of x. So du is going to be 1 over x dx. Try this again. So dv is going to be the square root of x dx. I looked at just this. And antiderivative here, you're going to add 1. So it's going to be x to the 3/2 and divide by that 2/3. All right. Now, a little bit better. So then I'm going to say 2/3 x to the 3/2 ln of x minus 2/3 x to the 3/2 times, you can write it as x to the negative 1 dx, right? And these also simplify here. Just add them, right? 3/2 and negative 2/2 is x to the 1/2. So I have 2/3 x to the 1/2 here. So I have 2/3 x to the 3/2 ln of x minus, I'm going to add 1, right? So that again becomes 3/2. And then I'm going to divide by that, so multiply by 2/3, which becomes 4/9. And then plus c. Smaller. So I would say u equals x squared, du equals 2x dx, dv is your cosine of x dx, and v is just sine of x, right? So I would have x squared sine of x minus sine of x times 2x dx. And again, I have to integrate a second time. So my u here is going to be 2x. My du is going to be 2. dv is going to be sine of x dx. And v here is going to be negative cosine of x. So I have x squared sine of x minus, and I like to put this in brackets because that helps with positives and negatives. So I have 2x negative cosine of x minus the integration of negative cosine of x to dx. If I do my negatives here, this turns positive, right? And then when I distribute, I get x squared sine of x, and this turns positive, right? Plus 2x cosine of x, but I have to distribute that negative again, which is going to flip it back to negative, right? Antiderivative of cosine is just sine, so 2 sine of x plus c. So I usually do